Concrete is found everywhere in the modern world. Our infrastructure depends on this deceptively simple material. Concrete is considered a commodity, a gray homogeneous product that is routinely mixed together and used where necessary. But concrete is actually one of the most complex materials used by man. Its structure is complicated and random over 9 orders of magnitude of length scale, as we will see in this video. When seen at a length scale of meters, concrete does indeed seem to be a simple, homogeneous mass. However, as we zoom in on the material itself, its complexities become apparent. This cutaway view of a typical concrete is about 50 millimeters across. Concrete at this scale is a composite with a cement paste matrix and inclusions called aggregates. Now let's zoom in again by a factor of 500 or so. This picture is a few hundred micrometers wide, and we are seeing the cement paste matrix of concrete. The matrix itself is a composite material. The lightest features are the largest unhydrated cement grains still remaining at this point of hydration. The gray regions are hydration products, and the darkest regions are capillary porosity, which is the water-filled space in between the solid material. If we zoom in on the gray shell around the large grains by a factor of 1,000, we see the structure of the main hydration product, calcium silicate hydrate. This is the glue that holds concrete together. This picture is only a few hundred nanometers wide. Even at this level, concrete is a random composite with a complex pore structure. So from length scales of meters all the way down to nanometers, concrete is a complex and random composite. The microstructure we have seen is important because it controls the behavior and properties of concrete. Let's first focus on the micrometer or cement paste level and see how the microstructure forms. These unhydrated grains are themselves random composites even before hydration begins. Using X-ray analysis, we can show the principal chemical phases of Portland cement. In this picture, C3S is red, the main phase of Portland cement. C2S is blue. C4AF is orange. C3A is green, and gypsum is yellow. Hydration causes these particles to dissolve and new material to form, greatly changing the capillary porosity. We use percolation ideas to describe these changes. Percolation refers to a change in connectivity of a material phase. This simple cartoon of percolation uses square grains. The blue background phase is at first continuous, or percolated. As the grains grow, the blue phase becomes disconnected. If the capillary porosity is well connected, there is an easy pathway for ions from corrosive road salt to reach reinforcing steel in concrete. When water is consumed by the hydration process, the connectivity of the capillary porosity can be lost, reducing permeability. At the millimeter length scale, concrete is a random composite of aggregates embedded in a cement paste matrix. The interface between aggregates and cement paste is very important. This region is called the Interfacial Transition Zone, or ITZ. It is a region of higher porosity, less cement, and more calcium hydroxide. Consider this simple model of a cubic aggregate surrounded by spherical cement particles. To see how the cement packs differently close to the aggregate, the model is first flipped over. Then we fly through the cement towards the aggregate. This final slice is taken right in front of the aggregate. The middle region shows extra porosity because the cement particles cannot pack themselves efficiently near the surface of the aggregate. It is sort of like pouring marbles into a jar. Toward the edge of the jar, the marbles pack themselves much less efficiently with more porosity. This is often called the wall effect. Now 70% of the cement has hydrated. More black porosity and blue calcium hydroxide can be seen in the ITZ than in the bulk cement paste. The unique microstructure in the ITZ causes different material properties. The ITZ around a single aggregate is shown here. The width of the ITZ is usually about 10 to 50 micrometers. In concrete, the aggregates are so tightly packed that up to 1/3 of the matrix volume can be composed of ITZ regions. An important question is, do these ITZ regions percolate? In a 3D model, we can measure the fraction of the ITZ regions that are part of a connected path through the material. This graph shows how much aggregate must be present for the ITZs to percolate. At about 35% by volume, the aggregates are close enough together so that some of the ITZ regions just percolate. At 50% by volume, most of the ITZ regions are connected to each other. Typical concrete has about 70% aggregate, and so will have percolated interfacial transition zones. Capillary porosity should not be confused with entrapped air voids, bleed water, or entrained air voids. The entrapped air void shown in this picture results from poor consolidation. Bleed water moves through fresh concrete during the first hours and can collect under aggregate or rebar as shown in this picture. The gap under the rebar is due to bleed water and can be a site for corrosion in the future. Entrained air is put into concrete on purpose to provide frost resistance. Voids and entrained air are important factors in real materials that can have great influence on properties. The microstructure of concrete helps us understand why processing techniques and admixtures work. In concrete, one of the chief ways to engineer microstructure is to alter the ITZ. For example, if we look at a fracture surface of concrete, we find that the cracks generally run around the aggregates through the ITZ regions because they are weak links in the microstructure. We can densify the ITZ by adding mineral admixtures like silica fume or fly ash to the concrete. The small particle size of silica fume will improve packing and provide silica to densify the ITZ by chemical reaction. The picture on the left shows the ITZ in a plain cement concrete. The picture on the right has 20% of the cement replaced by a mineral admixture. Notice that the small admixture particles are packed closer to the aggregate surface. Now 70% of the cement has hydrated. It is easy to see that there is more brown solid material and less black porosity in the model with the admixture. This makes the ITZ denser and stronger. Fractured concrete containing silica fume shows crack patterns that run directly through aggregate grains rather than around them. The ITZ regions are no longer the weakest links in the concrete microstructure. We have seen how concrete is a random composite with a complex microstructure over length scales ranging from meters down to nanometers. At every length scale, percolation and composite ideas can be used to describe the microstructure. Our understanding of microstructure is the key to controlling and improving the properties of concrete.